students. This video is on combination machines. It's something we talked about briefly in class, but here we're going to spend a good bit of time talking about how you do these machines for languages that have more than one property in their descriptor. For example, look at this first paragraph. Suppose you want to create a finite state machine that accepts strings with a multitude of properties, such as strings that contain BAAB. Hold on, let me get my cursor going here. I'm always losing it with this system. Okay. So here we have strings that contain BAAB. Where are you, cursor? All right, here we go. Contain BAAB, but don't contain ABA. Have even length, and contain no more than 7 B's. Now, if you try to put all that together at the same time as you're building the machine, you get your brain twisted in too many different directions. It's really difficult to do. Let me erase some of my scribbly marks. And so what we do is we separate it and draw a machine for each piece of the pie. So you would draw one machine for strings that contained BAAB, another machine for strings that didn't contain ABA, and so on. And then you would use this algorithm we're going to learn to put them together into one machine. Now, instead of starting with that 4 different property descriptor for one language, we're going to simplify it down to just strings that contain BAAB and strings that do not contain ABA. And that's what we have here in these two little machines that are drawn on the page. The first one, the one at the left, is for strings that contain BAAB, and I believe you can see the backbone of the machine here, I just can't write with this system. BAAB. There's the backbone. You know how to draw those machines. And then you say, okay, what edges are missing, and you add those, and that has been done here. You would start out doing the exact same thing for strings that don't contain ABA, but you'd think positive. So you would do the case for strings that do contain ABA, and that's been done right here. Here's the backbone, ABA. You can see that. And then we have added the missing edges, and then we flip the states so that the non-accepts became accepts, and the accept state became a non-accept state. We're going to leave that trap in the machine. Let me erase my squiggles, and you know what I need to do. I need to make this cursor bigger so I can see it just a little bit better. There. Alright, so here go the squiggles, and I want to show you how to combine these two different machines into one machine. And the steps of the algorithm are down here. One thing that's important to note is that you need to make any traps in your machines that you're combining explicit, so that there's always a way to go on A and on B from every state that's in the machine. So the steps of the algorithm say, number 1, make a start state that combines the 2 start states of the original machines. And make that be the start state. Come up here to this page, and you can see that I have done that. Right, I need to make this cursor bigger also. Here we go. This state right here, state 1A, is the combination of state 1 from over here with state A from over here. I just put those two names together. It's as if, remember that algorithm when we were running non-deterministic machines, we talked about being in more than one place at a time. Well, it's kind of like I've got one guy over there and I've got one guy over here, and they're going to proceed through these machines, and the states over here are combinations made of where the first guy is and where the second guy is. Alright, so then we say, alright, if I get an A from this combined state of 1A, where am I going to go? Well, you go look at your machine. You say, where did this guy go on A? Well, he came back to 1. Where would this guy go on A? Well, he would go over to B. So I'm going to erase these guys so it doesn't get confusing, because now we have a guy in, I forgot I can erase my original image too, so I got to be careful. We have a guy in 1 that went back to 1, and the guy that was in A went to B. So we're going to combine states 1 and B and go there on A. On B, from 1 we go to 2, and from A we go to A. So we combine 2 and A, and that's where we would go on B. Now we just keep this up until we stop turning up new states. Then we decide which states to make accept states. And that depends on whether you're trying to do an AND of the original conditions, in other words, an intersection machine and an intersection really are the same, or whether you're doing an OR, aka union machine. That changes the states that are accept states, but the layout doesn't change for those two different characteristics, either the intersection or union. So let's say, where do we go from 1B? Well, 1 on A goes to 1, and B on A goes to B. So we go right back here, 1 and B on the letter A. Where do we go from 1 and B on B? Well, 1 goes to 2, and B goes to C. So on the letter B, we're going to go to 2C. Now, what about this state 2 and A? Where do we go on the letter A? 2 goes to 3, A goes to B. So we need a 3B. That is what I said, wasn't it? Let me double check. 2 on A goes to 3, A on A goes to B. Yep. Now what about 2 and A on the letter B? Well, 2 goes back to itself, A goes back to itself. So here we go back to state 2A on the letter B. What about 2C? 2C on A goes to 3D. On A, from there we go to 3D. And from 2C on B, we go to 2A. We go down here on the letter B. Okay, well, I guess we'll do 3B. 3B on A goes to 4B. Okay. Goes to 4B. And on the letter B, 3B, goes to 2C up here. All right, now let's do 3D. On A goes to 4D. Three D on B goes to 2D. I never know how to lay these things down on paper to make them pretty. So they just end up being what they end up being. Okay, so let me double check that. 3D on B went to 2D. Yep. All right, 4B on A goes to 1B. Oh dear. All right, here. Good heavens, that's terrible. But whatever. 4B on B goes to 5C, and we don't have that yet. So on B we go to 5C. All right. Now, this machine's getting kind of big, so I say to myself, how big could this thing possibly get? And you tell me, how big could it possibly get? Well, there are 5 states in the first machine and 4 in the second. So when you're combining into pairs, you could get, it's like making a cross product set with tuples, that's kind of the same thing. We could get 20 different states, but hopefully we're not going to get 20. So far we have 5, 6, 7, 8, 9, 10. Hopefully not too many more. All right, so 4D on A goes to 1D. Oh, brother. 1D. 4D on B goes to 5D. Oh, brother, again. All right, 2D on A goes to 3D. We already have that. And 2D on B goes to 2D. Right back to itself. 5C on A goes to 5D. 5C on B goes to 5A. That was a growl. On B goes to 5A. Okay, 1D. 1D on A stays there. And on B goes to 2D. Down here. Alright, 5D. Oh, good. On both letters, just stays right there. And finally, 5A. On A goes to 5B. Oh, seriously? Double check. 5A on B. Oh, sorry, on A. 5A on A goes to 5B. Yeah, seriously. And 5A on B goes to 5A. Hopefully we have only one more state to do. 5B on A stays there. And on B goes to 5C. Okay. Now we're finished with the layout of the machine. Going back to the beginning, we were trying to make, I believe, an intersection machine. So let me go back over here and scroll up so we can see what the spec said. Make a machine for their intersection, strings that do contain BAAB and do not contain ABA. All right, an intersection machine can only say, yes, I accept, when the string has both properties. So in other words, it has to be in an accept state in the first machine and in an accept state in the second machine. The states that are possible accept states for us are 5A, 5B, and 5C. So we look around in our machine and see if we see any of those. 5A, yes, right here, this is an accept state. And 5B is an accept state. And 5C is an accept state. Okay. Looks like this state 5D is a trap state. Once you're in 5D, you can't get out of it, and it's not an accept state in the intersection machine. Sometimes these machines are not minimal. You could clean them up. It looks like Yeah, I'm guessing you could definitely get some shrinkage going on this thing. Um, sometimes I say that and I turn out to be wrong, but I'm just thinking I could. What if we were doing a union machine? These were the accept states for an intersection machine. Both the states only an accept state in an intersection machine if it's a combination of two accept states. But if it's a union machine that you turn this into, you have a lot more possibilities of accept states. Anything that's accepted by the first machine or accepted by the second machine needs to be an accept state in this machine, or it needs to go to an accept state in this machine. So the accept state in the first machine is 5. 5 paired with anything would be an accept state in this machine. 5 whatever. And in the second machine, A is an accept state, so anything paired with A. B is an accept state, anything paired with B. And C is an accept state, anything paired with C. So you would have a lot more possibilities here. We would add this state 5D. It would not be a trap state in the union machine. It would become an accept state. The start state would be an accept state because think about it, lambda does not contain ABA, so that turns to an accept state if we were doing union, and so would a lot of other things. So like 2A and 5A, we already said that. 3B, 1B, 4B, anything with a B, anything with a C, so 2C, and we already have 5C. We'd have a lot of accept states in this machine if it was a union machine. Now let's go to the next page. Let me get rid of these two and pop up this one and this one. All right, so just following along here, making sure I haven't omitted anything. Once you finish the layout of the machine, find all the states that are combinations of two accept states because you're making an intersection machine, and make them be accept states, la 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 la. Which states would be accept states for a union? We said a bunch of them would be. Now, make up a reasonably, it should say, sized problem involving 3 properties that can be solved by creating a combination of 3 machines. Write down the specification of the problem and then show its solution. Here's a framework. All right, so let's keep it simple. How about, let me make sure my font is, or my cursor is visible because I'm having some issues seeing the thing. And this one too. All right, so how about even length strings? Even length, that'll be one property. How about starts with A? And does not contain BB. So we will draw 3 separate finite state machines, and we can solve the problem in 2 phases by combining the machines 2 at a time, or we could combine them 3 at a time. I think I'm going to do 3 at a time just to make it go a little faster. It's a little bit harder to keep track of, but we can do it. All right, so let's go over here to this blank spot, if I can find my cursor. Where are you, cursor? Okay, we're over here in this blank spot. And I'm going to draw a machine for even length. Zero's even, so this is good. And then if I get a character, A or B, I will go to this state. Another character comes back over here. All right, I'm going to call this state 0 and 1. Second machine starts with A. So here we go, starts with A. B is going to take me to a trap state. I need a A and a B out of every state, so I'm going to make the trap explicit. Starts with A, and then once I have started with A, I'm good to go. So anything else just keeps me right here. I will call these states J, K, and L. And then I need not BB. Alright, so I'll do the backbone for BB. Once I'm here, I'm good to go. But remember, I want not BB, so eventually that's going to be the trap state. If I'm here on A, go back to thinking positively. Strings that contain BB. If you're looking for a BB and you get an A, you got to hang out here. Just keep looking for that B. And if you get an A here, that kind of wrecks things, so you got to start over again. Alright, then these are my except states because I'm doing the not BB. Okay. Oh, what am I going to call these guys? I'll call them X, Y, Z. Okay, now I'm going to combine all three machines at the same time. So my start state is going to be 0JX. 0JX. Where do I go on A? I go to 1KX. 1KX. Now, in case you're lost and you don't know how I'm doing this, what I have to do is see where you go on A from state 0, that'd be 1. Where do you go on A from state J, that'd be K. And where do you go on A from state X, that'd be X. So you put all those three together, 1KX, you make a new state. So what about the letter B from 0JX? I would go to 1LY. 1LY. Now, did we say whether we were doing an intersection or a union? Let's do a union. Oh, union's going to have a lot of except states. Oh well, let's just do it. So this union would be either strings that have even length, or strings that start with A, or strings that do not contain BB. I'm not sure that it's going to reject anything, but we'll see. So we're doing a union. Alright, so now from 1KX on A, we would go to 0KX. 0KX. Let me double check myself. On the letter A from 1, I go to 0. On the letter A from K, I go to K. On the letter A from X, I go to X. So 1KX goes to 0KX. Now 1KX on B goes to 0KY. And that's a new, no, wait a minute. That's this state. Oh, this is 0KX. Don't get mixed up. I need now one for, okay, let me do this again. Where am I going on B from 1KX? I'm going to 0, K, Y. Yep, 0KY. 0KY. Alright, now do 1LY on A. 1 up here on A goes to 0. L goes back to L. 0 L X. 0 L X. And 1 Ly on B goes to 0 L Z. 0 L Z. Okay, this is a little scary. Usually I have you guys all double checking my work. Now I'm all by myself. I could make a mistake. I wouldn't even know it. Alright, 0kx on A. 0kx on A goes to 1 k x. I already have that state, and that is over here on A. Alright, and 0kx on B goes to 1 ky. 1 ky. I don't see that one. 1 ky. Okay, now 0 ky on A goes to 1 k x. Well, that goes back over here on A. And 0 ky on B goes to 1 kz. 1 kz. Okay, now 0 Lx on A goes to 1 Lx. Let's see that. 1 Lx. And 0 Lx on B goes to 1 Ly. 1 Ly. We have that. It's over here. Alright. It's kind of a cute little machine. Okay, 0 Lx on A goes to 1 Lx. That'd be here. Oh, sorry. Oh, see, that was bad. Okay, here. Wait. Control Z. Okay, let me do this again. Let me go back up to my brush. Alright. 0 Lz goes to, on A, goes to 1 Lz. 1 Lz on A. 1 Lz. And 0 Lz on B goes to 1 Lz. Wait. Yeah, okay, that makes sense. Both letters are the same. Okay. Now, these last four maybe. 1 ky on A goes to 0 kx. 0 kx, that's here on A. Okay. Now 1 ky on B goes to 0 kz. 0 kz. I don't see that. 0, K, Z. All right. 1 KZ on A goes to 0 KZ. 0 KZ. Well, that's that one I just made. And 1 KZ on B goes to 0 KZ. Okay. Both of them go there. Interesting. Now 1LX on A goes to 0 LX. Oh, right over here. And 1LX on B goes to 0 LY. I don't see 0 LY. All right. 0 LY. Now 1LZ on A goes to 0 LZ. That's over here. And 1LZ on B goes to 0 LZ. So both letters are the same. Okay. We're getting close, I hope. I can only do 2 times 3, 6 times 3, 18. I'm getting up there. Okay, 0 KZ on A would be 1 KZ down here. And same for B. Yeah, so A and B from there. Down here, 0 LY on A goes to 1 LX. Back over here on A. And 0 LY on B goes to 1 LZ down here. Okay. Now, let's double check our work. Should accept any string with even length. Oh, wait a minute. We got to talk about accept states. So since we're doing union, any state that has a 0 in it, or a K in it, or an X, or a Y, those are all going to be accept states. So let's do the zeros first. Here's a 0. Here's a 0. Here's a 0 out here. Here's a 0. And here's a 0. Oh, this kind of makes sense because they're 2 apart. And evenness goes back and forth every other character. Okay, that's doing even length, looks like. Now this one's doing, starts with A. So it has to start with A. And remember it's an OR. So if it was an intersection, then only the strings that started with A would be good. So only these ones up on the top row would be good. But this is a union. So anything that's either even length or starts with A is good. So anything with a K in it now that's not already an accept state is going to become an accept state, like that one and this one. It's going to be funny if every state in this whole thing turns into an accept state. I would have done a whole lot of work for very little. Alright, so none of these have K's. Alright, anything with an X in it that's not already an accept state. Yeah, this guy. These are for strings that do not contain BB. Anything with an X in it that's not already an accept state. Anything with a Y in it that's not already an accept state. Yep, here's this. tell me we have one state in this whole thing that is not an accept state. Okay. Now, if this is true, then the path to get to this state should be for a not good string, like BBA or BBB. BBA, BBB. Those should not be good strings. All right, they don't have even length, they don't start with A, and they do contain BB. So yeah, I see those are not good strings. And you could get out here to this state and then come back on a B because you contained a BB at that point. Anytime you, well, no, because you could have that other property. All right, so the path that goes out to this state is BAAB, and then if you get a B, what went wrong? BAAB. So that's a good string because it has even length. And it does not contain BB. But as soon as you add this B to it, if you add an A to it, then that goes back here, and that's good. It's good because it does not contain BB. Yeah. But if you add, instead of A right there, if you add a B, then suddenly it does contain BB, and you've gone bad. Now, you can recover from that bad string if you get one more letter. Like if you're here in the non-accept state and you get one more letter, then you've gone to even length. Whether it's A or B, you've gone to even length, so now you're good again. I don't know if this machine could be minimized or not. It's an interesting machine, isn't it? So yeah, I picked a good set of 3 things. It's very interesting. So maybe some of you want to play a little bit more with that. I think by now you've probably gotten the algorithm just fine. Do we have any more in the worksheets about this algorithm? Let me go look. I don't think so. Nope, I think that's the end of this algorithm. So I'm going to stop recording here, and I thank you very much for watching.